detail. All right, so let me give you some examples of this so that we can start thinking about it in a serious way. So atomic structure. Okay, so it's all about electrons. All the interesting action happens with electrons. And again, we call these E minus, or sometimes just a plain old dot to make things really simple. And so, oops, yikes, that happens more than I would like. Sorry about that, everybody. That's better. Everybody always starts with hydrogen. It's a cliche, but it's a good, useful cliche. So hydrogen structure, I'll write this up and then explain it. So there's a nucleus in the middle. It has protons. That is the symbol P+, and there's one of them. And their neutrons, just N0, they have no charge. There are none in the nucleus of the hydrogen atom. And then orbiting around that is an electron, one lone electron. And there are some rules. Basically, this is an electron. There should be the same number as protons. So the atom is neutral. And you can write this as just plain H dot if you like. Right? And for scale, let me put this in a different color so it doesn't get too confusing. The nucleus, if this is the size, of a sand grain, the atom is about 15-foot diameter. Okay? And so there's a couple of features of that. So if you're talking about a hydrogen atom, you could zoom in so that the nucleus is the size of a sand grain. The whole thing is sort of 15 feet diameter would just barely fit down front here. So most of all your atoms is empty space. The only reason you have solidity is because those electrons are moving so fast that it gives sort of the illusion of solidity. But if somebody could line everything up, you could easily pass through us. Right? As far as matter goes, we appear solid, but most of us is empty space. Again, because the nucleus is a little itty-bitty thing in a big cloud of electrons. And again, the reason why we appear solid is because those electrons move really, really fast. It appears like a sort of cloud of negative charge. Questions so far? Yeah. Is that size ratio just for hydrogen atoms? It's approximately true for other atoms. Actually, it's even bigger for other atoms because the inner shell is 15 feet out. The next shell is even further out. So, in fact, it's even more dramatic. And the nucleus doesn't get a lot larger. Or, well, comparatively speaking, 2 sand grains is not a lot bigger at this size scale than 1. But it's roughly speaking the same. All right. So let me go further. So what about more complicated atoms? So the rules for electrons in atoms. Because again, why do we care about this? Because if you know where the electrons go, you know the structure of the atom, you can predict its properties. So number 1, they orbit the nucleus in shells. Okay, number 2, the first shell holds up to 1 pair. Oftentimes, pairs of electrons matter, so we count them in pairs. You'll see why in a little bit. The first shell holds up to 1 pair of electrons. That is 2 E minuses. This third rule, I should do it this way. The next shell holds up to 4 pairs. That's 8 E minus. Now, There are further shells. We will not worry about them in Bio 111, but there are further ones for making even bigger atoms. You fill shells from inside to the outside. 4, there's this thing that got named by Wolfgang Pauli. They call it the bus seat principle. You see it every day on the shuttle bus to UMass. That is, when filling a shell, you first put one electron in each pair, and you only complete a pair when you have to. And all of these things together, they predict atomic structure. So why is it the bus seat principle? You know, when you load on the bus to go to the T, unless you're sitting with a friend, and electrons don't really have friends, typically you see people fill those empty pairs of seats one at a time. You don't sit next to someone unless you have to, right? I mean, in humans it's a little more complicated. If it's somebody attractive, you want to get chat up or something like that, you might do it. But electrons, again, they're not attractive. They don't worry about those sorts of things, right? The other thing is, the electrons are not also antisocial. They don't have free will. It's an energy-related thing, right? The physics of that I actually don't know, but it's certainly explainable. In any case, we'll see how these rules work in a second, that you don't make pairs unless you have to. And so again, like I said, I'll show you that in a sec. All right. So again, I want to put up a bunch of rules, and you're thinking, oh my God, all these rules, can we please get down to some biology? We will eventually today to get down to, well, maybe not quite biology, but at least some applications of this stuff. So there's a couple things. Atomic structure predicts atomic properties. All right. And why does that matter? Because it's going to matter how the molecules work. So number one thing we can predict from all this stuff is the number of covalent bonds an atom will form. You might want to know that, because it's covalent bonds, it determines how a molecule forms, it determines what its shape is. So the number of covalent bonds an atom can form is actually a very big question. Turns out the rule is that atoms want to have their outer shell filled and will share electrons to do so. And that sharing of electrons is a covalent bond. We'll talk more about that later. All right? And again, atoms, they don't have free will, they don't have desires, they're really very simple things. Want is a shorthand for it's energetically favored for them to have a full outer shell. Right? And so it's easiest to think about it in terms of want. They will share electrons in order to achieve a filled shell. So like the first shell with 2, the second shell with 8. And that sharing is covalent bonds, which is a big deal from what we're concerned about in biology. So that's a tip of a very interesting iceberg. The next one is far weirder, and you'll just have to trust me that it will turn out to be important in a few days. This is this thing called electronegativity, or EN for short. And that's how strongly an atom holds onto its outer shell electrons. All right? And you think, oh my, why could that possibly matter? The answer is it turns out to make a huge difference in what we'll see in a couple days. Electronegativity depends on what's called kernel charge and some other stuff. But kernel charge is equal to the number of protons in the nucleus minus the number of inner shell electrons. Right? And I can explain why that makes any sense in just a second. And that's the charge that an outer shell electron sees as it orbits the nucleus and inner shell electrons. All right, so let me explain that. Remember I said nucleus, right, grain of sand, first layer of electrons 15 feet out, that's probably here somewhere. The next shell is 50 feet out, so it's out in they're orbiting way up near the back row of this auditorium. And remember, the nucleus is staying put more or less, and the inner shell electrons are whizzing around so much that it's like a cloud. You've got like a big ball of charge right here. The people in the back row, you can't see the nucleus. What you see is kind of this 15-foot blob here, and its net charge. That is, so you have +3 in the nucleus and -2 orbiting it. The net charge is -1. So way out there, I'm sorry, +1. So way out there, what you're seeing is the net, the sum of the charge on the nucleus and the inner shell electrons. That's what you're actually influenced by. So the kernel is this little thing in the middle, and the net charge on it is the charge on the nucleus added together with the charge on the electrons. So is it the number of protons subtract the number of electrons, because electrons are negatively charged. So it's like what the people in the back row see when they don't have their good glasses on as they try to look at the nucleus in close. Right? And again, oh my goodness, why would you care about that? It turns out it will be very important. Trust me. So it turns out that higher kernel charge and other factors that they'll fuss about in chemistry more lead to higher electronegativity. And you can see that. If the kernel has more positive charge, then those electrons in the back row are going to feel more of a tug. It's proportional to the charge. Smaller kernel charge, I'm going to hold on to those electrons less tightly. Bigger kernel charge, I'm going to pull them more strongly. That's going to turn out to matter big time, as I said, in a couple of days. What I want to do is some examples of this, because I think that's a good way to think through these things and apply these principles. So I'm going to have you guys do them and talk to your neighbors and all that. We'll do 2 atoms one by one. All right. The first one I want to do is carbon. Okay. And carbon, I should make it a little bit. In the nucleus, there's 6 protons and 6 neutrons, it turns out. And carbon is going to, so what I want you to do is follow the rules I gave. Inner shell, 2 electrons. First of all, how many electrons are you going to need? You start filling. 2 in the inner shell, how many in the outer shell? Are they going to be paired? Are they going to be sitting together on the bus? Are they going to be spread out? That sort of thing. So there's going to be an inner shell and an outer shell. How many electrons in each?